and explain the geology of that field. Now, we did that in 10 minutes, so it could be right or I could be way off. But it uses a number of the things I've talked about here. We just sat down and worked it out with his well log and his seismic section. And so it obviously, with only spending a few minutes, it's generalized, but it gives you a good starting point to think about what your reservoir might be geologically and where you might want to put your wells. So that's what he's preparing something now for what we talked about at the morning break. And it's always nicer, I think, when somebody like me can come and present with your own data rather than my data. And so, I like to give workshops too, like that, where we just sit around and look at each other's data and stuff like that. So, so he's preparing that at any rate. So I'm going to carry on while we're waiting for him. And we left off here just to illustrate there's lots of good outcrops of this Woodford Shale. And so we've studied all of these that are shown with the arrows and the circles. And they've given us a very good idea of what the geology of the Woodford Shale is. Now, just to give you one example, I'm going to take you now to this area in blue. And look at this area in blue here. And what you see, here's the ground surface here. Okay, there's the ground surface, the modern day valley. And the Woodford Shale is broken into three members, what we call the lower member, the lower Woodford, the middle Woodford, and the upper Woodford. That's kind of a standard terminology that's been used for many, many years. Underneath the Woodford, stratigraphically underneath, you've got a rock unit called the Hunton Group, and it's a limestone. And then above the Woodford, you've got another group called the Sycamore limestone. So you've got the Sycamore on top and the Hunton on the bottom. And then there's another unit that occurs near the base, and that's the green shale. And then you get a green shale at the top as well. So that's the stratigraphy. Now, this is in a quarry, and what you see, this picture here, in the is looking down. This is a drone survey. We use drones in our work now. That's one of the newer technologies for outcrop geology, is using drones. So what you see here is a drone survey that we did. So you're looking down at this outcrop, and this cross section here is the one shown in white there. So you see, looking down, we've got stratigraphically lowest, we've got the Hunton Group. We've got the Hunton Group, and then the lower Woodford, middle Woodford, the upper Woodford, and then the Sycamore limestone. Okay, so let me go back now and make a point that I made before. This one here, that here's the Woodford Shale. The area in yellow here is the Woodford Shale. This, if you're not familiar with what these are what we call stratigraphic charts that show the stratigraphy, the rock stratigraphy, with the oldest rocks down here and the younger rocks up there. The Woodford Shale, we're good? Okay, the Woodford Shale sits on top of the Hunton limestone. There's the name for the Hunton limestone. And what is meant by these sloping lines is that's geological time at which you had erosion. So you deposited the Hunton limestone, then you had a drop in sea level, actually for a very long time, that created a big erosion surface on the top of the Hunton limestone. And then sea level came in, you had marine transgression, and that's when the Woodford was deposited. So like when I've said before, the Woodford is really a condensed section, is deposited during that marine transgression on top of the Hunton unconformity, which was formed during the preceding drop in sea level. So we have something like this. Here's our sea level curve again. We drop sea level. We well, let me add to that. 1 second here. Okay, so let's do our sea level curve like this. I'll make 2 cycles here. And during younger time over and towards the right, and the Hunton limestone was deposited during one of these this high stand here. And then during the falling stage, the Hunton limestone was eroded. The top surface was eroded, so you have an unconformity surface or a sequence boundary that formed then. And then on the turnaround, that's when your transgressive shale and your condensed section was formed, and that's what the Woodford is. So the Woodford Shale sits on an unconformity that represents a long time period between deposition of the Hunton limestone and the Woodford Shale. Big unconformity. Very important. Okay, so here we have now then, here's the Hunton group, or the Hunton rocks, and the Sycamore, and the Hunton was deposited. I'm going to do a little sea level curve again. The Hunton was deposited here. So that represents this deposition. Then you had the drop in sea level to create the unconformity. And that's represented right here. Then you had marine transgression. So you first deposited this green shale, and then the lower Woodford, the middle Woodford, and the upper Woodford. They were deposited on this transgression. And then you've got an upper green shale that probably represents a high stand deposit. We're still not quite sure about that. And then you had the Sycamore limestone deposited on top of that. Okay, so that's your sequence. That's where you have your unconformities, or your unconformity is right there. And once we recognize that, we can explain and understand the reservoir and why it had the properties and the production that it did. So, if we just let's look at some of the properties. One of the things that we do is we describe the rocks with thin sections and just looking at them with by hand. And in this case, we found 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different rock types that made up this shale. And let me back up. There's one thing I should tell you. The shale, about the stratigraphic thickness is about, I think about 300 feet. So 300 feet of shale. And in that 300 feet, we found 12 different rock types. So it's not just homogeneous black shale like we used to think. Now, half of these turned out to be soft rocks, very fissile rocks, and soft so that they were not brittle, so they didn't break very well. The other 6 they actually had more quartz in them, which made them hard and brittle. And so geomechanically now, we've got 2 geomechanical groups of rocks. One where you get good fracturability because the rock is hard and brittle, and the other group is doesn't break very well because it's more shaly and more clay rich, so that it bends rather than breaks. Bends rather than breaks. So that was the first finding. So what we would want to do would be to focus our effort into finding drilling sites where we had the brittle rock, where we could actually get in there and fracture the rock. The fissile or soft rocks are the ones that had more clay and actually had more organic matter as well. So geomechanically, these rocks were not brittle, they were ductile, they bend, but they contained the organic matter that went in to make the hydrocarbons. Whereas this group of rocks was brittle, turned out to be very highly cemented, so it did not have much hydrocarbon in it. Okay? So but it had the good geomechanical properties, but bad geochemical properties. So the first screening method that one usually does is just to see what you got in your reservoir is the TOC, or total organic carbon. And so if you were to measure total organic carbon in these rocks, they'd be pretty high. They were deposited with clay-rich, with these rocks here that are all clay-rich. So clay-rich meaning very low sedimentation rate, and that's when you get organic matter deposited, the dead organisms and things like that fall to the seafloor. The fissile rocks that have more quartz were a little higher energy deposits, so you didn't have much in the way of clay, and so the rocks were brittle, and but because they were higher energy, they had less total organic carbon. Okay, so that's the next fact that we found. So now we're starting to understand that our reservoir is going to be complex. Now, here what you see is, here is a very handy tool that anybody who looks at outcrops should have one of these. It's called a gamma ray scintillometer. And what it does is it measures natural radiation. Just like a gamma ray tool measures it in the subsurface, this tool, you hold it in your hand, you hold it up against the rock, and it measures how much natural gamma radiation is being emitted. Yeah.
So, for example, I have an outcrop of shale zone here in Bolivia. I could just go with this scintillometer and kind of like use it as a help in some way.
Yep. Yeah. And then what you could do is, well, here's the outcrop gamma ray log for that stratigraphic section. Okay. For this section here, we did that with our scintillometer. At, I believe it was every half foot we took a measurement. And this is the gamma ray log that we came up with. We call it an outcrop or a handheld gamma ray. So what you could do, for example, to answer your question, you could go to an outcrop of shale, you could do this, and then you could sample areas. For example, I would want to sample areas or stratigraphic intervals that had a high gamma ray. They're the ones that are going to have TOC. So you take a sample here, and you measure the amount of TOC, and then you calibrate it. This is the gamma ray reading, X counts per second this is in, and you've got Y amount of TOC. And you may want to say, well, what's the minimum amount of TOC? That's going to be in a cleaner rock, the ones that are more brittle, that have more quartz. So you might take a sample right there, and you'll usually find a low TOC. So you can take enough samples to calibrate. And like in this case, I might take a sample here, and one there, there, something like that, where I get a range of gamma ray counts. I determine the TOC content, and then I can calibrate that to the rest of my gamma ray log, my outcrop gamma ray log. So we did that. That's what we do routinely in our outcrops. And we also, as good geologists always do, we measure the stratigraphy, we measure the stratigraphic section, and this is a very generalized one, but what it shows, sand is yellow, or excuse me, quartz-rich rocks that are brittle are shown in yellow, and the gray rocks here that are more ductile are shown in gray. So now we've learned something else. We've recognized now that the lower part of the Woodford is more clay-rich, and your brittle rock, your quartz brittle rock, is getting more abundant and thicker bedded upward. Okay, so no longer do we have a uniform black shale by any means, and there's systematic stratigraphy here. Could we put this into a sequence stratigraphic framework just with this data? Well, you could. For example, you've got this, remember this pattern here that it gets transgressive and then it goes regressive. Okay, so you got a sequence boundary here, transgression, look at your well-logged way it's behaving. Then you go regression. At some point you're going to have another sequence boundary, maybe there. You get a nice blocky log pattern. And then a shale, it's going to be a maximum flooding surface, and then a little high stand deposits there. All because you can do this because of the log shapes, just like we've been doing. So now we've determined there's a sequence boundary. There's a condensed section, a maximum flooding surface is going to be, there's one here, and there's one down here. Okay? So, without all the colors now, we've got, well, let's see, let's do. We've got a fining upward trend, transgressive, and then it reverses itself, regressive or progradational. So that turnaround point is our maximum flooding surface in our condensed section. So that's going to be an area, potential area for good hydrocarbon accumulation. Then we go up here and we see a blocky pattern. So because this is high stand, you've got a sequence boundary here, and then you have a low stand down there. And then a condensed section and maximum flooding surface right here. And then you see that cleaning up trend there. That's another high stand. Another big drop, you've got a sequence boundary just below here, somewhere below, actually right about, sequence boundary right about here. Then you've got a finding upward. Here's your maximum flooding surface, and then you get your high stand deposit. See those shapes? Once you determine those shapes, it's a piece of cake to do a sequence stratigraphy interpretation. So let me just finish this, and then you can go ahead, Julio. You ready to? Okay. Yeah, let me just finish this little bit, and then I can do that. Then you can do that. So you see, I've developed a sequence stratigraphy for the shales. So same principles that I used before. Okay, this is where did you go? Left. I was going to say this is a good place to stop and let him make his presentation. But he disappeared again. Well, I'll go on with this, and then by that time he'll be back and we can stop. Okay, well, we have another instrument, a tool that we use. And the acronym is, oh, you're ready. Okay, you ready to?
No, go on. When you tell me.
Yeah, now's a good place for me to stop and you to start.
Okay.
Put you on the spot here.
Can I use your computer?
Yeah. Sit back there and drink my coffee.
The idea is to have some argillaceous or siliceous shape for the rich content.
Right, the silica is what gives you the brittleness.
But the problem, I was going to ask you that, since they are soft, it's going to be hard to fract. So,
Well, if you've got a really thick section, that's true, and drillers don't like to go drill into those rocks. But that's where your reservoir is. Those are the rocks that are going to fracture. So you've got to say you got to drill there. Okay, that's your reservoir. I'll explain more of that as we go along. But yeah, there's always kind of a battle between the geologists and the drilling engineers. Drilling engineers just want to drill more footage, make more money that way. Geologists want the data.
Okay, thank you. Well, good afternoon. First of all, this is like an overview of something that I have presented before, and this was an idea that I've been talking with my colleagues, you guys, about 2 months. And basically what I wanted this morning was asking Dr. Slatt his opinion in order to continue a development program. So it's only a draft, of course, because we
maximize the screen.
Yeah. Right away.
It's over on the right. Yeah.
So of course this is only a draft presentation for us to look into. So I called it the upper and lower detected stratigraphic framework characterization, integrating with a little of reservoir engineering that I've been studying. We're going to look at the geography, the reservoir characterization part, the reservoir engineering that I can explain further, and some of the conclusions after Dr. Slatt's opinion. So, as you may know, the Carrasco football project actually is in the middle eastern part of Bolivia, which is right here in the department of Cochabamba. Here. Right here. And well, what we're trying to do is to find out what's the stratigraphic framework for this project. Well, I tilted a little the map here because what I wanted to show was how the positional sequence could be interpreted from north to from north to south, given that that's the positional sequence that we've been studying this morning with Dr. Slatt. One thing that you may know is that the Carrasco football project has always been producing from the Llantata formation, which is below the Petaca, and it was not quite as good reservoir as the Llantata, but the Llantata was a better reservoir than the Petaca formation, traditionally because these wells were producing from that and deeper wells of the boundary. We're talking about Cretaceous formations. So, a little bit more by looking at this picture is that we have the Carrasco field in the hanging wall and the Carrasco football part, of course. And the project is to find out if the graphic framework or the depositional sequence will continue in the south part of the reservoir. So, this just shows the well-off of the Llantata formation, which is below the Petaca, just to show you that it was always being conceived as a better reservoir, and it has traditionally the three wells of this model, the Carrasco well 3, the 2, and 1, which is northern, has always been producing from the Llantata formation. So right now, the three wells aren't producing anymore from the Llantata formation. So the project was to see another opportunity. Okay, I'm going to take a moment to open a file, which is correlation, done right after the Carrasco football was developed. So what we're looking now, we have to remember that the northern part of the field is here. This is the southern part of the field, and this well is between them, but on the west part. Okay, so we can see in the correlations that the Llantata formation was always the main objective, and on the Carrasco football 1, we have seen gas shows evidence of gas during drilling on the upper Petaca and the lower Petaca formations. So the first question was, before the intervention of this well, if these two reservoirs would be connected. That was an assumption that we did at the beginning of the project, and it was come to our surprise that they had different reservoir pressures. So we had to think what the seal was. It might be more of a stratigraphic field seal.
Well, the bottom one had lower pressure than the upper.
Yes.
So, which is the opposite, so you could expect compartmentalization just by that.
And I have a well-logs here that shows that in a better way. Just another picture of what this work was done by Misael, whose geological model was developed for the intervention project on the Carrasco football 3. Okay, another file that I wanted to show, and it was very important for us this morning, was to show the structural section of the well while it was being constructed. Let me show you right here. So we have a vertical well. This is the Carrasco football 2. Both have been drilled from the same well site. And the Carrasco football 3 has entered a minor fault, which we're trying to develop the Llantata formation and now the Petaca formation. it is very important to understand that the project that I want to develop with my team is like coming this way, like in the southern part. If we were to come out from the screen. So so this is the important part of the presentation: how to develop the sequence stratigraphy and the sequence boundaries on the well log, using the well log. A little bit of reservoir engineering information is that 4,034 psi of reservoir pressure was measured here, with 12 hours of shut-in, and 4,812 psi was measured with pressure transient analysis, also 12 hours of shut-in. And it is an unstable value, but we should hope pressures, higher pressures downside. This is almost the original pressure that we were expecting to find, so it was considered as like a discovery. And the lower reservoir pressure that we found here, it was associated that it might be connected with another part of another structure. Why is this important? Because this is not overpressure. If it were overpressure, we would be talking about some geomechanics drives that may have caused the overpressure here, but this is not overpressure. This is just normal pressure, but originally. So, and also the fluids were a little bit different. As you can see, the gas-oil relationship of the upper part is about 1,522. I'm sorry, that's the production. I have here the gas-oil relationship is 13,300, and this is 7,090, which means that this is a lighter reservoir, a lighter fluid, closer to a gas, a wet gas. Actually, it is a wet gas, but more closer to a dry gas, and this is closer to a volatile oil. So this braiding is heavier as a fluid. No, it has not been measured over that time the density of the petroleum that now we have. I'm sorry, it cannot be measured anymore because this part actually is closed, and we are producing from the upper part only. From the reservoir engineering point of view, these are the results of the lower Petaca as an identification of the reservoir model. What we have here is the pressure and the pressure derivative curve, and this is from the upper Petaca. But the thing is that we only have 12 hours of shut-in. If we had more, like 48 or maybe 60, we can confirm how is the behavior of the last part. Why is this important? Because one can think that it could be a reservoir by faults, or it could be a reservoir that's between a channel, depending on the slope of this last line. So for the moment, I remember that we reported a closed system between faults. And after Dr. Slatt's class and his how can I say this, and his recommendations, this might be a different model. And I'm going to try to show that. Please go where the well testing shows. Okay, so that's a background of the project. Now, what we have to remember is that the Carrasco Football project, where do we start doing our characterization? We need to define where the landware or the seaware would be, as we have learned. So we already know that the Carrasco Football 3, which is this well before drilling, we have already tested that this is positive and this is positive too. And the Carrasco Football 1 has never been tested. Right now it's closed, and we have evidence reasons that we could test this part in order to see the lateral continuity of the reservoir. So, well, this is a satellite image of where the well is located, and we have reason to believe that if, you know, I'm not a geologist, first of all. I don't know how the geomorphology of ancient times were very accurately, but I have reason to believe that we can extend that the shoreline could behave this way for the Cretaceous formation, of course with some differences. But my point is where to define where the landward place would be compared to the seaward, which we define it as this. The landward would be at this plan, at the northern part, and the seaward direction will be on the southern part for the Petaca, for the Carrasco football field. So that's on the same model, just drifted from east to west. And well, now we're going to look at the well logs. What we did this morning was to define the sequence boundary from the bottom. This is the Naranjillos member from the Cretaceous as well, which is traditionally known as a shale. And we can see an upward trend on the gamma ray from here, which has been defined as a transgressive system track, until we have defined the maximum flooding surface, which is the highest peak point of the gamma ray here, and a new start of the trend in the characterizations of the sand. So we will have a high stand in this part, which of course we have seals here, which could explain the difference in pressure of the lower Petaca and the upper Petaca. And this high stand is showing us that we have lower energy, right, in the sea level core, and that would explain the depositions of more sands. And after that, we have a new sequence boundary here, where we can see the depositional sequence of a shale. We have a new transgressive system, and with this new high stand, where we have new energy, then we start to have this part on. We will see this part of the curve of the sea level activity, which we're gonna start having the positional sequences of sandstones with very low shales in between. These are thicker parts, which could explain that the water was entering an incised valley, and where it started to fill up channels of the reservoir. I have a seismic interpretation.
Can I add something to that? Or?
Yes.
I had it a little bit different. I think I was scribbling so much that it's close, but I put the sequence boundary here.
Okay.
And this would be, so you had a sequence boundary, you had down cutting, erosion, and then you had the formation of your incised valley during that falling sea level. And then when sea level started to rise, you backfilled with incised valley sands. It's just like that first exercise you guys did, where first we did a stratigraphic datum, and then we put it into structure. So I put the, where you get that sharp change, I put the sequence boundary at the base of the sand. Now it doesn't seem like much difference, but it is. But still, you've got the shale down here, which is going to effectively separate the upper sands from the lower sands. Okay, and that's why you get the different pressures,
yes,
and so on. And let's see, the other thing, the high stand. See, I put another little sequence boundary right about in here. You got transgression, regression, another little sequence boundary. These are these high frequency cycles, and another transgression and regression. But again, those are small, they probably don't matter that much. But I would move the sequence boundary up just a little bit, but still so it's kind of sitting on top of the shale.
So you're right, because gamma rays is getting out.
Right. Right, yeah. So that's why I think you have the different pressures and different reservoirs and different depositional environments.
That would be the seal.
Yeah.
Okay. So looking by the seismic, we have to remember that this is the Petaca formation that we're studying, and the Carrasco Footwall 1 may see part of the same channel. What I'm trying to explain is that we're having a system a little bit like this. If we had a cut here, we're having a cut. We might have a channel in an inside valley where we're having deposited the sandbars, point bars. And why does the shape of the Petaca formation over the Carrasco Footwall 3 horizon is different than the one? Because that may be defined as, if we have the point bars over this side, we're going to have the mud blocks over this side and the higher energy, and it would be the opposite on the other side. A little bit like this. So the Carrasco Footwall over the Carrasco Footwall 3 well would have this interpretation about the point bars and the one over this. Unfortunately, the well is not very centered, we could say, on this part, and we have traditionally thought that this will not be a structure at all. But if we think this is a meandrous river or a channel, it could be really big. So I think it could be bigger. So I think that a 3D seismic work will help into the interpretation of this. Was one of the conclusions.
Well, why did we make that a meandering channel? Why did we do that? What was the important thing that we saw? Very subtle feature. The asymmetry and steep side, point bar side, right?
Yeah, that's why I drew this on different sides.
Why don't you show it on the seismic line?
Okay, I have that.
Really? Oh, good. Okay.
I did
even better. Great.
Yeah, I did a zoom so I can show that point. This will be the point bars maybe of the Petaca formation on this part of the.
Do you see that on the other side for the? That's cool.
Well, actually, that's the project. We want to see if this will continue on the other side of the fault.
And what about on this side?
Well, it's not really clear, but if this would be a meandrous river where this would be a plug where, this part where we don't see the reflector.
Okay, but what about the shape? What he's asking, go back to the seismic. What about the shape on the left-hand side one now?
Another photo más grande. Can you go to the other picture?
Yeah, go to the left one, yeah.
That one.
Yeah. Now what about the shape there?
Well, this is the part where you will be feeling the blood, right?
Well, the channel, and where's the point bar?
I can see that it could be right here.
No. This is the steep side, and the shallow side is getting thinner. So this is your point bar over here. Over here, it's just the opposite, where you've got your channel, and then you're thinning your point bar. And that's why when you drew that picture, you've got those 2 point bars pointing at each other. Because in the 3rd dimension, you'd be coming around. Okay, your channel is coming around in the 3rd dimension. So that can be one channel. Right?
And the interpretation is that this may continue, of course, on the other side of the fault. I know that's
well, while you've got that up there, let me make a point that this is pretty subtle features that we're looking at. You, if you look closely, you can see that you've got a steep side and a shallow side, but it doesn't really hit you really hard. It's subtle, and again, it goes back to the idea of pattern recognition. If you've got some idea of what you might anticipate in the depositional environment, and here in this case, I think you see it. You see the point bars pointing at each other, and in the third dimension, you would have your channel coming out of the third dimension. So if you do a 3D seismic horizon, it should pop right out at you, if that's correct.
So one of the conclusions is that we have reason to believe that behind the structural fault, there might be continuity of the inside valley for the upper Petaka formation, and of course hopefully a lateral seal of this fault that could be effective, or if we're talking about a meandrous river, we could have the seal because of the mud blocks that could form in this sedimentary depositional environment. So, well, that slide of course is out of place. These are the conclusions that I just worked through lunch. First of all, we have a project up to north that will be the Carrasco Football 1. We should see if there's continuity of the meandrous river of the Petaka formation, seizing the opportunity that the well is already closed. So for us, it's only a perforation job. Then the second conclusion will be that the inside valley and the depositional sequence could be found southward of the structure, behind the fault. The Petaka formation has proved hydrocarbons in the upper and lower stratigraphy, and there's differences in reservoir pressure, which means that the seal between these two is because of the sequence boundary that we have defined as a shale, so it would be more of a stratigraphic seal between these two, of course. The Carrasco Football Sur project can be elected for traditional Llantata as well, because this is only for Petaka. We have the upsides that the Llantata could be also accumulated in this part. And it is imperative that 3D, with the acquisition of the new 3D seismic in this area, we could work in a new horizon time slice to determine this hypothesis, to prove this hypothesis. And as a reservoir engineering perspective, I would recommend longer shut-in time hours to define the channel, characterized as a well in a channel reservoir in the late time part of the derivative. So that's pretty much it.
Well, happy drilling. Go ahead.
We're gonna work more with this.
To me, it all makes sense. If I see patterns and they make geological sense, then there's a good chance you're correct. If you see things that you have to kind of fudge things in here and there, then it's probably not correct. I think in this case, I didn't see anything wrong with your interpretation there. It all looks geologic to me. Pressure differences, your fluids, the shapes of your channels, cross-sectional shapes going in opposite directions. So within the third dimension, you've got a meander loop and all of that. Yeah. So I think that's a good working model to go by. And you probably change it or modify it, or improve on it, but I think that's a good starting point to work from.
Yes, I was thinking where I could start while we're having the geological interpretation here. is to pinch out this part of the other well at the northern part and try to test the continuity, either for reservoir pressure or reservoir modeling and pressure transient analysis. That should be easy and not too expensive as, you know, having a new drilling rig program for this part of the well. But still, I think there are reasons to continue studying this project.
Great.
That's it. Thank you.
Okay. And I'll just make the point again that there's not a thing that he said that I haven't shown you examples of. Everything was in different parts of the lectures and things, but all there, the shapes of the meandering rivers and all that stuff.
What do you propose?
Seismic.
What do you propose was the future steps for this project?
To test the Carrasco Football 1 Petaca and see if they're lateral or continuous. And if that, while the guys working the seismic model, drill another well in the south. As an exploration.
En vez de probar, ¿no queréis hacer análisis de los propios de ambos pozos? We could do that, right? We have one on the side of the fault, the other one on the side of the fault. We can look at the cuttings on this.
Well, the interval of interest, I think we figured was what, about 20 milliseconds or something?
Yes.
So I don't know what that would convert to in feet or meters, but you might not get a good representation of cuttings. You might just get a couple of intervals or something, depending upon the thickness. If you take your cuttings at 10-meter intervals, you might just get a couple of cuttings, you know, so it wouldn't do you much good, I don't think, other than to look at the rock type. You could certainly look at the rock types in the cuttings and see if they're the same, but that would be pretty qualitative if you did that. I think you're better off spending your money just looking at, you don't have to spend much money at all if you're looking at the 3D seismic if you've got it. Look at that, do your horizon slicing, and just refine your sequence stratigraphy based on the log shapes. Yeah. Well, actually, we do know the thickness here, I guess. It's
This is the science.
the whole thing is about 150 meters, so yeah, you get some good cuttings if you do 10-meter cuttings. So you have about 15 sets of cuttings, and that might be worth looking at. Yeah, that could be worth looking at.
And one thing definitely we should do if we go ahead with the drilling program is take courses.
Well, yeah, that
For
would
example.
certainly tell you a lot. You would spend less money sitting around discussing a log than you would spend by spending the money to take a course. Okay? In other words, you sit as a group, you spend X number of hours, it costs so much money, you guys get paid, and sometimes that takes longer and you still don't have a positive answer. But if you take the core, or even a borehole limit log, and I haven't talked about borehole limit logs, but that's cheaper, and you can often use that to find these differences. Yeah. So that's what I would do at any rate. Okay, well, let me get back to the shales. And take a break in just a few minutes. So I just started to talk about an instrument that we have called X-ray fluorescence spectrometer. Big fancy name for a relatively simple instrument, an X-ray fluorescence spectrometer, or XRF for short. Okay? And this is the instrument. It's not very big. You can hold it in your hand. And in fact, it's got a handle on it. It kind of looks like a gun. So you can take it out in the field and you can actually make measurements on the field. There's some problems with doing that, so we don't do that anymore, but we used to. But some people do that. They take this out to the field, hold it against the rock, and then they get a measurement. Well, what are they measuring? What they measure with this instrument is the chemical composition of the rock. And if you hold the rock here on your core, for example, and you press the button, you get a full chemical composition of your rock at that one point. And here you see some core. We've got core laid out here. And we do our measurement, and it's so quick to make the measurement that we normally do it at maybe a 6-inch interval, or sometimes even less than that. So all you do is you take the instrument, the XRF, and you put it down on your rock, and you press a button, and out comes your chemistry of the rock. And you can't read this, I'm sure, but these are all the chemical elements. On the horizontal axis, the vertical axis is depth in a well, or on a core in this case. And why you want to do this is, first of all, it's quick. You can take lots of measurements in a short period of time, but why do you bother to take these measurements in the first place? Well, it turns out that that minerals, are made up of chemical elements, and certain elements are in some minerals but not in other minerals. So you can convert the chemical analyses, how much aluminum, how much sodium, how much silica, how much sulfur, and so on. You can convert those to minerals, abundance of minerals. So let's look at this picture here. This is from a publication, and what it shows is common minerals in a shale. Like one is called illite, it's a clay mineral. And so the horizontal axis is the mineral illite, and the vertical axis is the element aluminum. And aluminum occurs in illite. And what you can see here is a very nice straight line relationship, that the more aluminum you have, the more illite you have. So you quantify it. You quantify by taking out a measurement of the aluminum at one spot. You're quantifying how much illite you've got in your rock at that one point. Calcite, a common mineral that's in shales. So your horizontal axis is calcite. It's made up of calcium and carbon and oxygen. So here's a plot of the calcium content, and once again you see a very nice relationship between the amount of calcite and the amount of calcite and the amount of calcium. Ca is calcium. So you measure the amount of calcium right there, and you can make an equation out of this. This is the closest a geologist ever come to doing an equation. Doing a straight line linear regression, right? That's about 3 words for me. So that's about as close as we ever come. So at any rate, by measuring the calcium content, you can determine how much calcium, the mineral calcite you have. Molybdenum, this one down here. I don't quite know what this is, but here's the molybdenum curve. as a function, oh, I see what this is a curve of total organic carbon, TOC, versus molybdenum. Well, there's a linear relationship again. Well, it turns out there's not, organic matter, that is your TOC, does not contain molybdenum, but the sediments in which you often find the organic matter has molybdenum in it. So you measure the amount of molybdenum and you can make an estimate. Once you've developed this curve, you can make an estimate of the TOC content. Well, I can guarantee you, if you've ever sent samples out, like cutting samples, for example, if you've ever sent them out to have analyses made with other techniques, principally another technique called X-ray diffraction, where it's another technique for determining the mineral composition, but it's more complicated, it takes a longer period of time, and it's more expensive. So you may take all your samples and send them off to a lab and say, tell me the mineral composition, every 1 meter or whatever. And you sit and you wait and you wait and you wait, and 3 months later you get your results back. By that time you've forgotten why you sent them off anyway. So you're on to another project or something. So this technique is very rapid. You just go through and I think it takes about 30 seconds, I think. You hold the XRF gun on the sample for 30 seconds and you get a complete analysis. You go up a certain amount, hold it another 30 seconds, and you get another complete analysis. So that's why you do that, but also in the process, because it is so fast to do this, you can take a lot of measurements in a short period of time. If I had one of these instruments and said, I want to do 1,000 analyses so I can determine the mineral composition. Well, if I went to the boss and said, I want to do 1,000 X-ray diffraction mineral analyses, which are expensive, time-consuming, and so on, you're going to get kicked out of the boss's office, okay? But with this thing, you can do 1,000 analyses in a relatively short time, a couple of days maybe, and you've got the whole thing done. And once you buy the instrument, it's inexpensive to run the analyses. Now the instrument costs about $50,000, but like we bought one, my group, and we've made that money back many times over just by all the analyses that we can do. So not only is it good for determining the mineral composition, but it's a fantastic correlation tool, doing this X-ray fluorescence to get the chemical composition. And that's really what I want to show you. But first let me finish up what I was just saying there. It turns out that certain elements are derived from minerals from land, and other ones from the ocean, other ones are wind-blown, and some are from organisms in the ocean. For example, you tend to find, when you find titanium, here's the chemical symbol, Ti for titanium. When you tend to find titanium, it's in a mineral called rutile, titanium oxide. And it's a very, very small mineral, but very heavy. And it tends to be found in wind-blown deposits. So here's the cloud blowing the titanium into the ocean. Titanium gets there and it sinks to the seafloor. And so that's an indicator when you find titanium in your sediment, it's an indicator that you had wind-blown sediment deposited. The elements zirconium, to a lesser extent titanium and silica, tend to be in part derived by land material, by erosion, of material on land, and so that material comes down the river, gets transported to the ocean, and it sinks to the bottom and gets incorporated in the sediment. So the element zirconium, for example, is an excellent indicator of river-borne sediments. So something like that. Now in the marine environment, you've got all these little microfauna, and here's a picture of a microfauna that is in the Woodford Shale. It's called a radiolaria, it's called, and it has a silica skeleton. What you're looking at here is a picture of that silica skeleton. Well, one of the things you look for to find out if you've got a good shale or not so good a shale, if any of you have read or studied anything about shales, you find that one of the things that people are always wanting to know is how much silica is there in the rock. And the reason they want to know that is because that's what gives you the brittleness. Okay, it's that silica, it's a rigid mineral, and it's in part derived by organisms that have quartz or silica skeletons, and when the organism dies, it falls to the bottom and accumulates silica. But there's a problem there because you can also get silica from land. So sometimes it's difficult to figure out how much of that silica is derived from land. If you make a measurement of the total silica content at a spot in your core or in your outcrop or whatever, it's difficult sometimes to determine how much silica is derived from land and how much is derived from the organisms. Yeah.
What would be the big difference between that silica itself?
Oh, I'm glad you asked that. That was a lead-in. It's a big difference because what happens. Okay, I'm gonna go the next step of detail here. You deposit the silica skeleton, but chemically that silica skeleton is kind of weak. It's not totally crystalline when the organism was living. Well, that organism dies and it falls to the bottom and starts to get buried. And when it gets buried, the temperature and pressure increase, and you get a conversion of that, what was originally the kind of weak silica, to a more rigid, stronger silica. And the grains interlock. It's like welding. It's almost like welding. And the grains interlock, and that's what gives the rigidity to the silica-rich sediments that come from the organisms. Now on land, you often find the silica from land is mixed in with clays and things, and you don't get, and that silica is already undergone whatever change it's going to have, so it's not going to change when you bury it. And so that silica is going to be like whole grains in a clay matrix. So you don't get that welding effect. So it's not brittle. And it drives me crazy when I hear someone say, I got to know the silica content. Got to know the silica. Everything relies on the silica. And I say, well, what kind of silica are you talking about? Are you talking about the silica from the organisms? I'll call that biogenic silica. Or am I talking about the silica from land? I'll call that detrital silica. And somebody will look at me like I'm crazy. You know, who cares? What's the difference? But it makes a big difference in your fracturability, in your brittleness and your fracturability. So it's important to try to figure out in your rock how much of that silica is from detrital and how much is from the biogenic. Well, can you do that? Sure, it's really easy to do. For example, you cut a couple of you cut a thin section. You look down the microscope and either you see those little biogenic organisms, the remains of the organisms, or you don't. Or you see like a quartz grain or something like that that's made out of silica. So when somebody says, I got to know the silica content, what am I going to do? I've run, well, okay, let me back up a minute. You take those 1,000 samples, we'll say, and you submit them in for X-ray diffraction analysis, which measures the mineral content. All that tells you is the total amount of silica in your rock. It doesn't tell you how much is biogenic and how much is detrital. And so somebody goes crazy. I just spent $100,000 doing these 1,000 analyses, you know, and it told me I've got silica. So what, you know? And I say, well, did you cut a thin section and look at the rock? Look at the rock? You know, I don't look at rocks. I look at the computer. You know, I look at databases. And so that's the simplest way. You look at a rock, you spend $50 to have a thin section cut of the rock. You look at it under the microscope, you can tell. Another way to do it is with this X-ray fluorescence technique, the XRF technique. And because silica, here's the symbol for silica, Si, it can be either detrital or biogenic, and so a dual origin is possible, but it's even a little more complicated than you see here, because silica also occurs in other minerals, like the mineral feldspar. It contains some silica, but it also contains aluminum. Now, this silica here it's really, the chemical element is silica, but the mineral is called quartz, a common mineral. So quartz does not contain any aluminum, but things like feldspars contain both silica and aluminum. Potassium, here's the symbol for potassium. It's present in feldspar, and it's also present in clay minerals, and illite the clay mineral. So and aluminum is contained in clays as well. And you've also got some silica that occurs in the clays as well as in the feldspars. So what you really need to do is you just have to make a simple calculation to find out how much of that silica is, in relative terms now, how much of that silica was detrital in origin coming from the rivers, and how much came from the organisms in the ocean. And the way to do that is to just make a ratio of the amount of silica that you measured divided by the amount of aluminum. And the principle behind that is that you've got silica in all three of these minerals, clays, feldspars, and quartz, but aluminum only occurs in clays and feldspars and not quartz. So if you get a very high ratio of silica to aluminum, that normally indicates that most of your quartz came from biogenic origin. Okay? If you get a high ratio or a low ratio, meaning a high amount of aluminum, that's an indicator that you had a lot of your aluminum came from the river. So a lot of your quartz came from the river too, a lot of your silica. Okay, so it's really an easy, kind of a difficult concept maybe, but once it connects, it's really a simple thing that you do, just a simple calculation. And so you can take that then, and you can make a depth plot of silica versus aluminum, silica over aluminum, and pick out which intervals are going to have the biogenic silica, which will have the detrital silica, and then you can say that the ones with the high biogenic silica are prone to fracturing, and the ones with the low biogenic silica are more ductile, because they've got the clays mixed in with them, clays and the feldspar. Let me just show you this one example, then we'll take a break. So this is a really simple, very simplified profile from this X-ray fluorescence. We have a name for that. We call it chemostratigraphy. Chemo for chemical, and then stratigraphy for the stratification. So here we have in this plot, we have depth in a well or a core. Well, you have to have rock samples. Well, no, I'll take that back, never mind. And so down here in the horizontal axis, you've got gamma ray, then you've got titanium, zirconium, and now I've got the silica to aluminum ratio. I've got calcium, I've got potassium, and I've got aluminum. Okay, when well, in this particular case, this is a little bit different because this is a set of rocks that don't have, let's see, how am I gonna, this is a set of rocks that have a lot of calcite in it. And how do I know that? And what's the distribution of the calcite? Well, I look at the calcium, and I see a peak right there, I see a peak right there, I see a peak there, peak there, and a peak there. By the way, rocks that have a lot of calcium in them, the mineral calcite and another mineral called dolomite, they're brittle too. Okay, so this is, I'm showing you another example that really doesn't deal with the silica here. We're dealing more with calcite. So, I see these high peaks of calcium, and then I go next door here and I look at the potassium. Potassium has a low peak here, very little here, very little there, very little there, and very little there. I go over here and I look at aluminum, very little aluminum, not much, none, not much, so on. So how do I interpret this? Well, how I interpret this is that these intervals where you get the high calcium and the low potassium and aluminum, they're intervals of calcium carbonate, okay? And when you get a lot of calcium carbonate in a rock, it too is brittle. Silica isn't the only thing that gives you brittleness. And so I now have a brittle interval here, and a brittle interval there, and a brittle interval here, and a brittle interval there. Okay, remember I also said titanium and zirconium are two elements that are detrital, and you see those have very low concentrations, just like the calcium, just like the potassium and aluminum. So you look at these elements, and you can pick out your mineralogy, and then you can convert that to what your geomechanical properties are going to be. And if you've got core, you measure the geomechanical properties, Poisson's ratio and Young's modulus and so on, and then you can calibrate to the X-ray fluorescence, and you can build a geomechanical log of Poisson's ratio and Young's modulus once you have a few calibration points. So let's take a break, and then I'll show you an example of the silica aluminum ratio.
So, if we have rocks more biosilica, what do we do? Can we assume also that we're going to get problem with it's just a safe activity, but since you say the trees will go well there,
Right. Lower porosity. And also lower TOC. The TOC is going to be organic matter that's associated with clays, as they fall out. So when you get a high river input, that's when you get the clays, and that's when you get the TOC as well.
What about in this case, just the position? I'm going to have a good layer of position of the ocean. They're going to be mixing with the silica.
Yeah, you get some TOC. But less.
Will the TOC compromise the welding process that we were talking about, the position process?
Yeah. It'll start to mature. Going
So I'm reducing the porosity, I'm using the porosity, which is less space for TOC.
Right.
So what I'm
And
looking
you're converting your solid organic matter to liquid or gas.
So what I'm looking for is the idea will be a combination with high biosilica for brittleness, but with enough silica, non-biosilica for the source.
So let's talk about geomechanics. The source is going to be ductile. So the ductile rocks are your source rocks. Your silica ribs are your reservoir.
Esta relación
That's why
alfa
you
es
want to
bio,
drill
es al
into the
revés.
reservoir, into the
La
fracture of
relación
the rock.
que se calcula acá
The
en
idea is to do that.
digo que cuando es alfa es creo que bio o es petrita.
So below,
Bio,
as
es
the
bio,
hydrocarbons come up
que
in the
tiene más
fracture.
cantidad de
And the same is true for
orgánico.
calcite.
Está
Mineral
bien,
calcite, mineral dolomite. So in this case, here, it's not silica, but your brittle zone is going to be here, here, there, there.
They work inside the shell.
Son libros.
They could be as
It's a layer. It's just like what do they call them? A hard streak. When the word hard streak, those are usually calcite, pure calcite that doesn't have any clay. We often find them in this muddy.
What I remember we used to deal a lot in Liverpool was ash.
Yeah.
I don't know if you heard about that, but we used to have some little thin ash layers. They will work.
Eagle fur.
Yes.
You get a lot of them. Yeah.
They will work as kind of like trap, seal rods inside the shell.
Yeah.
The problem with the ashes, they will fracture them and then close immediately, right?
Yeah.
So they
So
will kind of
when they hit water,
and then they
they
fall.
expand.
So
It
in
comes
place.
right up, yeah. So, see, in this case now, see all of this stuff that's got, all of this here that's got no calcium, and it's got high potassium, high aluminum. That's going to be your organic rich shale. So here's your source rock, and there's your reservoir rock above and a reservoir rock below. If you drill, yeah, well, it's a layer. It's a layer.
But a lot of people don't understand that I'm not only the shell, but inside of the shell, I have my source shell and my reservoir shell. That's what I need to convince them that not all the shells are trapped. Inside the shell, it varies.
And that's why when you said TOC is 1.5, I said it doesn't mean anything to me. Suppose you take 4 samples. You only have enough money to do 4 samples. So you take a sample here, you take one there, take one there, one somewhere else. You get high TOCs. Wow, great reservoir, but or great source rock. But suppose now you say, well, I raised enough money for 4 more samples, so I'm going to take the calcite layers. Now all of a sudden your average goes way down. Okay. So that's why it doesn't mean anything to me. It all depends on how many samples. It's kind of like in a statistical value.
Well, this is the way I'm trying to do it. I'm taking techniques, right? I'm not going to calculate an average.
Good.
If this one has
Show the data.
1.5, this one has 3, it has 1.5. I would say let's focus now on between these. So from 10 meters, I'm going to 5 meters, 3 meters, 2 meters, 1 meter. 10 meters of shell would be good enough to get some good amount of
Maybe. Some of the layers are less than 10 meters, and you might miss them.
And you know what is interesting about this shell and looking specifically? This shell is on surface. You start drilling, you're already on shell. This shell has 800 meters thick. Since day one that we start drilling, we're at 50 meters, 150 feet, we're already detecting gas. Small, I mean, we use the GT, the units of gas through the mud loaders. At 50 meters, we're already having small detections of gas. And we have it all the way down. So we know there is some gas in there. If you have a chance later, I'll show you a little mud log. And you see that from this, and I wish I had my, I go to this field to do a lot of tests, and you can see the shell outcrop coming out. It's beautiful, it's so layered. It's just.
You need to invite me down to go in the field.
And you know what?
I'll bring all the instruments.
And I'll send you the picture.
Yeah.
It's just so beautiful. You see this shell that it's an outcrop, it's on the surface. You can see the layers. You see some intrusions in between. And as soon as you start drilling, you detect this little amount of gas, right? We don't go to the hundreds of units of gas detection. We detect 50, 40. But we're at 200 feet. Yeah, the pad, the drilling pad is on the shell side. It's an outcrop.
Yeah. Well, that's where you want to do your first work on the outcrop, so you get an idea.
Here is the issue. We're in the sub-Andean zone, so there is a lot of geographic movement. Try to navigate a directional or horizontal well is going to be an issue because, for example, we tend to put unconventionals in some flat areas where we can navigate nicely through a horizontal well. That would be a challenge. Yeah. If once we start mapping once we start doing stratigraphic correlation, we may see that this shell is not necessarily a flat shell because of all the folding. We have a in the middle of the mountains.
Yeah.
That could be a limitation for developing that unconventional.
Right. You got to know the structure. Yeah.
Yeah. Try to navigate a horizontal well through so much, deviation.
One of the things you can do in a case like that is use a dip meter log.
Dip meter log?
Yeah. Well, that's an old log. They're FMI, or borehole image log.
FMI, okay, FMI, yeah.
The old ones use tadpole plots. You know what a tadpole plot is?
No. Tadpole, which one?
Tadpole plots. Those are dip meters.
Maybe I seen it during my classes.
Well, people don't use them anymore because they have the borehole image log now.
What are they?
It measures the strike and dip of the bed.
Strike index.
Yeah.
So that will help me with my geomechanical.
Well, it'll help you with that, but it'll also use a maybe to work out the structure. If you got beds, if you got one area the bed's dipping this way and another they're dipping this way, you've got a seam line there. And that's what it tells you.
This reservoir, at least the reservoir rock which is below, we have it nicely mapped. It's a nice anticline.
Yeah.
It's very long. Let's say it goes like this, and it's long.
Yeah.
And the source rock, which is the shell I'm talking to you, above. I don't really know how flat it is, but it's on surface. It's close. Is the rock that surfaces. Okay, is the first. We only find three formations. We find this shale. Below that we have some shallow sand, and then we have the sand. We only go through three rocks, three formations. And we're talking about each one is around 1,000 meters.
Yeah. Oh.
So we'll have to see in these 1,000 meters, since it's the one that is in the surface, the geography is going to be missing.
Yeah. Well, has anybody taken surface data and extrapolated to the subsurface geology, strikes and dips and things?
Maybe. I'll check the geology.
Yeah. Because that's where you always start. You know, if you got an outcrop, you do your strikes and dips to see where that outcrop is going to be in the subsurface. You follow that trend into the subsurface. You probably do, yeah.
Can I ask you one question? Let me go back to the You said this one is around 50,000.
Yeah.
How much is gonna sit?
Oh, that is about 7,000.
That could be 5% of strong case, and will be able to justify $5,000.
Really handy. I've been using them for 30 years. The outcrop area log. It's a great way to tie your outcrop to the subsurface.
We accept donations from the University of Oklahoma. Such a nice institution. We'll take it.
I'll give it to you for 8,000.
Oh, come on, you're already in paying the price. You gotta pay customs on that too.
Sí, está bueno. Me puedo quedar. Creo que no. Sí, no se va a ver. Pero no así. Por lo menos no porque lo que nos diga.